So let's review what we've been talking about. So we've been talking about one central idea, which is hypothesis testing. So in hypothesis testing, we have some claim or idea we're trying to make a conclusion about. And that claim or idea has to do with the entire population. And so we want to make a conclusion about the population using one or more samples. So let's review with an example. Let's say in your next job, you're, let's say, head of marketing at some company, and you happen to know that your brand is really popular. Let's say that you're representing Coke or Nike. And so let's say that your idea or your claim is that your brand is so popular that let's say over 90% of the world has heard of this brand, has recognized this brand. And so let's say that you have a sample. You have an observation in the form of a sample. And let's say you sample 1,000 people from all over the world. And let's say that 971 people recognize the brand. So it seems like, so in your sample, what percentage of the sample of 1,000 recognize the brand?
97.1.
Yeah, 97.1%. So it seems like definitely your sample is consistent with this claim that over 90% of the world recognizes the brand. But the question is this far enough away from the 90% for you to say that it's actually true for the population? Or is this close enough to 90% where you can say that this is a natural variation of 90%, or if it's close enough to 88% and it's a natural variation, where you can say that the true percentage is actually 88%. So we want to do hypothesis testing to be able to make a conclusion about the whole population using this one sample. So let's go ahead and use hypothesis testing. Let's review. So what was the first step in hypothesis testing? Yeah, so first step was we want to identify the two statements, HO and H1. So to do that, we look at the original statement, our claim, and we can always generate a second statement in the form of the opposite or the counterclaim. So what would the counterclaim be here? Yeah, so the easiest way to generate the counterclaim is to keep the number the same, 90%, but just change the direction of the inequalities. Right now we have over 90%, which is strictly greater than. So the opposite would be everything left over, which is less than or equal to 90%. Recognize the brand. And so basically, in words, that's our claim and counterclaim. So we said that of these two statements, one will be HO and the other one will be H1. We just need to identify which is which now. So to do that, we need to convert each of these statements into mathematical statements. And because we're dealing with a proportion of success, or a proportion of something we're keeping track of, which is recognizing the brand, we're dealing with a proportion of success. So we're going to use this symbol P, proportion of success. But remember, our claim always involves a population measurement. So this is a proportion of success for the population. And our claim says that it's over 90%, so it would be greater than 0.9. So for the counterclaim, we're gonna use the same symbol P, but it's less than or equal to 90% now. So now that we have the mathematical statements, now we're ready to identify which one's the null hypothesis, HO. So which one did we say, how did we say to identify HO? Yeah.
The HO is the one that has like the equal sign in it.
Very good. The one that has the equal sign, so it would be this counterclaim in this case. This statement has the equal sign. And so we can say that this is involved in HO, and the other one automatically will be H1. But then technically speaking, we said that HO is only the equal sign, so you're gonna take this statement and basically just remove everything except for the equal sign, so it'll just be P equals 0.9. So the null hypothesis itself is P equals 0.9. And then the alternative hypothesis is the entire other statement, which is P is greater than 0.9. Okay, and so that was the first step, which is identifying HO and H1. What was the second step?
Assume HO is true.
Yeah, assume HO is true. And in this case, what is it that we're assuming is true? We're assuming that HO, which is P equals 0.9, is true. That means the true proportion of success, or the true proportion of people in the world who recognize the brand is 90%. And so now we're gonna visualize this with a distribution. And on the x-axis here, because our claim involves this variable that represents the proportion of success, we're basically going to use that variable regarding the sample, which is a proportion of success in this sample of 1,000 people. So the number of success, and a proportion is really a number out of the total. So because we're dealing with a proportion of success, we're looking at the number of successes out of a sample of 1,000 people. And again, success is what we're keeping track of. So in this case, we're keeping track of the number of people who recognize the brand. So if our null hypothesis is true, and P really does equal 0.9, or 90% of the world, then if we're observing only 1,000 of them, then how many successes should we expect to observe? How many people who recognize the brand?
900.
Yeah, it should be 90% of 1,000, which is 900. So at 900, we basically plot the y value, which is the probability of each x. And so we plot the y value by, at 900, we have a bar whose height represents the probability of that being observed. And that's the most likely, if this null hypothesis were to be true. And so as we move away from 900 in either direction, we should see the probability get less and less. Same in the other direction. So we have this distribution. We've talked about this type of distribution before. This is a binomial probability distribution. So if we were to identify the mean and standard deviation, what would that be of this distribution?
900.
Yeah, the mean is n times p, which in this case is also 900. And that 900 comes from n times p, where n is the number in the sample, which is 1,000. And then p is the true probability of success for the entire population of the world, which we don't know what it is, but there's a step in hypothesis testing where we assume that the null hypothesis is true, and in this case, it's p equals 0.9. So we're assuming that p equals 0.9. So that's how we're getting the 900, 1,000 times 0.9, and that's the mean. So what would the standard deviation be?
9.49.
Yeah, standard deviation will come from the formula, square root of NPQ, because this is a binomial probability distribution. So n again is the number in the sample, 1,000. P is the population proportion of success that we don't know, but we assume the null hypothesis is true, and that p equals 0.9. Q is going to be 1 minus p, which is 0.1. And so if we punch that in, what's the standard deviation?
9.49.
9.4, thanks. So this distribution has a mean of 900, and it has a standard deviation, or a measure of spread, or the average distance of all the numbers from the mean is around 9.49. Okay, so with that mean and standard deviation for this distribution, we're ready to also visualize the size of the tails of the distribution. So let's say that we want to make a conclusion with 95% confidence. So this will be given. So recall that visually, a confidence level means that the area of the body of the distribution represents that confidence level. So if the confidence level is 95%, that means that visually, the area of the body of the distribution is that number, 95%.
You're just throwing out the 95, right?
Yeah, that's given. So for now, this is given. But we've been saying that the confidence level is equivalent to the area of the body of the distribution. So the body of the distribution will be the same number, 95%. That leaves out the rest, which is 5%. That will be divided across the tails of the distribution. And we said that in hypothesis testing, we could either have one tail or two tails. So this remaining 5%, alpha, will be divided across the tails of the distribution. So how many tails are there in this distribution? One tail or two tails?
One.
Yeah, so the way that we can find that, remember, is to always look at H1, and then we look at the number of inequalities involved in H1, and that'll tell us the number of tails in the test. So because this is a one inequality, this is strictly P is greater than 0.9, that's only one inequality, so this is a one-tail test. So if it had been P is greater than 0.9 or P is less than 0.9, that would have been a two-tail test. But as it stands, this is a one-tail test. Not only is it one tail, but is it right tail or left tail? Right tail, very good, because it's the variable is greater than the number, so greater is to the right on the number line. So this is a right tail test. So that means that you can go ahead and draw out that one tail that happens to be on the right. So all the tails combined add up to this alpha, which is 5%, but there's only one tail, so that tail has the full 5%. Okay, so the area of the tail is 5%, that means that the rest, which is the body of the distribution, has the confidence level of 95% on it. So this body is 95%. Okay, so now that we visualized the tails of the distribution, let's go ahead and incorporate the observation now, which is the 971 that we observed on the sample. And so basically, the name of the game is the observation in the body of the distribution or the tail of the distribution? And, so the way that we're gonna find that, determine that, is basically to calculate test statistic and compare it to the critical statistic. So we have this observation of 971. Right now, I don't know whether it's in the body or the tail, but let's say that I draw it somewhere close to the tail and then I'll move it later if needed. So I'll draw it right on where the tail starts. So 971 here. So remember, the observation is gonna have a test statistic. In this case, because we have a bell curve, it'll be a z-test. And where the tail starts, will have its own z-score. That's a z-critical. So critical statistics always come from tables, and test statistics always come from a formula. And so let's go ahead and use a table to find z-critical now. So we're gonna use the z-score table to find z-critical. So using the z-score table, if we know the left area to the z-score we're trying to find, then we can find that z-score. So the total area to the left of this would be 95%. So find 0.95 as the left area, and then let's find the corresponding z-score.
And then, 1.645.
Okay, very good. So you should be seeing 1.645 as the z-score that matches up with a left area of 0.95. So 0.95 is the left area, so look up in the middle of the chart, the closest number to 0.95, and then find in the first column the corresponding z-score. Yeah.
Why is it 1.645?
Because we're looking for a left area of 0.95. If the left area had been 0.975, the z-score would have been 1.96. So. So you wanna look up this left area and look for 0.95 as the closest number. So that's gonna be, 0.95 is between these two, 0.94, 95, and this one. But this is searched for so often, that there's a star here that you can follow. And it'll have this exact 0.95, you know, correspond to that.
Oh,
Yeah.
okay, thank you.
Okay, any questions on finding this? Yeah.
I just have a question, why is that graph considered still a bell curve if the left tail is like so much more longer than the?
Okay, good question. It turns out that the way I drew it, it looks super skewed, but these values here have probabilities that are so close to zero that the actual distribution that you're gonna see, this is zero, so the actual distribution where the bulk of this is actually much more symmetric than the way I drew it.
Okay.
Okay, any other questions? Alright, so we found z-critical from the table, that's the 1.645. And then z-test is gonna come from a formula. We've talked about this formula. There's a classroom version of the formula that we talked about, and also a textbook version of the formula. They look different, but they'll give you the same result. So the classroom version was this. The textbook version or the homework version is this. You can use either version and get the same result. So let's plug in numbers. So X here is the number of successes. That'll be 971. And then N is the size of the sample, that's 1,000. P is the proportion of success for the population, the true proportion of success. That's gonna be assumed to be 0.9. And then you substitute the same numbers down here on the bottom. So if we punch that in the calculator, what do we see for z-test?
7.48.
7.48. So you'll see that z-test is a very large z-score. Okay, so that means our observation has a z-test of over 7. So is that to the left or right of this critical z-score? Yeah, it's definitely to the right. And this critical z-score is where this right tail starts. So everything to the right of it is inside this right tail. So that means that I can redraw it more precisely now and have the observation definitely in the tail of this distribution. So z-test is 7.48. So the observation is definitely in the tail of the distribution. So now we're ready to formulate the conclusion. And basically this is step 3, which is answering the question of, is the observation consistent with the idea that HO is true? And there's 2 ways to answer this question, either yes or no. So yes would imply that the observation is in the body of the distribution. No, the observation is not consistent with HO being true, means that the observation is in the tail of the distribution. In our example, the observation's in this tail of the distribution, so we can answer this question as no. This observation is not consistent with this idea that HO is true. So we have one observation that is already not consistent with this idea that HO is true. So what can we say about HO being true for all observations if already it's not true for this one? Yeah, it can't be true for all observations. Already it's not true for this one, so you can reject HO being true. So if we can reject HO, what can we say about H1? Yeah, we can accept H1. So both of these conclusions are true. One is just phrased in terms of HO and one's phrased in terms of H1. But we want to phrase it ultimately in terms of the original claim. So in this case, the original claim was HO or H1? It's H1 based on step 1 of hypothesis testing. So because we said we could accept H1, we're going to accept the claim. So the final conclusion is that based on our confidence level, 95%, we can say that with 95% confidence, we can accept the claim that over 90% of the world recognizes the brand, and there's enough evidence to already reach that conclusion. We don't have to observe anything else. We can flat out make that conclusion based on this one sample. Yeah.
What would our p-value be for this one?
Okay, we'll talk about that in a moment. Yeah. We'll talk about p-value in a second.
Why is HO being rejected?
Oh, because this picture here is the picture of HO. So this is what we see if HO were to be true. But we have this observation that is definitely in the tail of this distribution representing the HO. And because it's in the tail, we're saying that this observation is not consistent with this idea that HO is true. So if already we have this observation that is inconsistent with this idea of HO being true, then we can conclude that HO can't be true for all possible observations, or at least 95% of observations, if it's already not true for this one observation. So we can go ahead and reject the idea that HO is true for 95% of observations. And so that's why we can reject HO. And again, it'll help you remember and understand this if you think back to the sheep example that we talked about. The sheep example, our idea was that all sheep in the world are white. And we had an observation that was, let's say, not consistent with the idea, like we had in our sample, we had 5 gray sheep. Then in that case, already in our observation, it's not consistent with the idea that all sheep in the world are white. So because of that, we can go ahead and reject the idea that all sheep in the world are white, because already we've observed something inconsistent. Right, so that's why we're able to reject the idea, but in this case, the idea is HO, so that's why we can reject HO. And we can reject HO, accept H1. And because the claim is H1, we're gonna accept the claim. Any questions? All right. Okay, so here we reach the proper conclusion by comparing, in this case, 2 z-scores, a test statistic and a critical statistic. I'm starting to use the general language of statistic versus z-scores, because you'll see in a moment, or later on today, that in this example we're comparing 2 z-scores, but later we could be comparing 2 t-scores, or 2 chi-square values, based on what the underlying distribution actually is. But so far, in hypothesis testing, we've only talked about this underlying distribution being a bell curve, so that we've only been comparing z-score to z-score. But in general, we're going to compare a test statistic to a critical statistic. Okay, so far we've compared these 2 things. But in this example, we can say that with our given confidence level, with 95% confidence, that we're able to reject HO and hence able to reject the claim. But let's say that this confidence level had changed. Let's say it was given to you as a higher confidence. Let's say that you wanted 99% confidence. What would change in this example? What is it?
Alpha?
Yeah, alpha changes, good. So alpha now is always 100% minus the confidence level, which alpha is now 1%. And then what else changes?
The Z critical?
Yeah, very good. Because alpha changes, the size of this tail changes from 5% to 1%. And because of that, the Z critical that you found from the table, based on this this right area and subsequently the left area, also changes. So this Z critical goes from 1.645 to whatever Z score gives a right area of 1% and hence a left area of 99%.
2.575.
So if you look up a left area of 0.99, you should see 2.33. So the closest left area to 99%. So 0.99 is probably not directly in the table, but there's one that's the closest, and it should correspond to a z-score of 2.33.
It is. Unless I'm doing the wrong one.
Yeah, so remember this 99% is a left area. It's not the middle area where there's extra left tail here. So this 99% is a left area. So you don't want to use those bottom right numbers, those bottom 3 numbers, because that 99% corresponds to a middle area. Those bottom 3 numbers on the right side of the table, that would make this represent a middle area, but really this is a left area. So instead of this bottom 3 numbers, you want to use the main part of the table, which represent left areas. So look for the closest number to 0.99. Yeah, 2.33. So Z critical here would be 2.33. Any questions at all? So Z critical now changes. The position of where the tail starts changes. So instead of originally being here, now the tail moves to the right, and let's say it moves here. But does that affect our conclusion? No, because our z-score isn't affected based on the confidence level. The z-score doesn't change depending on the confidence level. The z-score is only based on the sample itself. And the z-score for our test observation is 7.48. So 7 is a really large number, so that's gonna definitely still be in the tail of the distribution. So even though where the tail starts shifts to the right, the observation is so far to the right that it's still in the right tail. So because of that, the conclusion is still the same. The observation is still in the tail of the distribution, so we still reject HO, we still accept H1. And the claim is H1, so we still accept the claim. So for 99% confidence, we still accept the claim that over 90% of the world recognizes the brand. What if the confidence level were moved up even more, at 99.999%? Can we still make the same conclusion?
Again, it's unrealistic for the population.
Yeah, so we know that we can't make a conclusion of 100% confident. But anything less than 100%, we can still have that confidence level. So what if the confidence level were 99.999%? Would the conclusion still be the same? That the observation is in the tail of the distribution, and hence reject HO, accept H1, and in this case, accept the claim. What do you guys think? So we said, we went over the case of 95% confidence, we went over the case of 99% confidence, but what if it were even higher, 99.99%?
Everything above 3.5 is 99.5.
Yeah, excellent. The observation has a test z-score of 7.48, which means it's already so far right that no matter where you define the tail, it's likely still gonna be inside the tail, because the observation is already so far to the right of 7.48. And the confidence level just adjusts where this tail actually starts. But you see in the chart that even with 99.99% confidence, or a left area, you see that the z-score is 3.5. So z-critical, even with 99.99% confidence, the z-critical is 3.5, and our observations of being 7 as a z-score is definitely still gonna be in that right tail. So the point is that because this test z-score is so high, that no matter what the confidence level is, likely we're gonna end up being able to reject HO and accept H1, even for very high confidences. Any questions? Okay. So let's go ahead and we were able to make a conclusion now based on comparing two values, the test statistic to the critical statistic. So now let's go ahead and make the same conclusion by talking about the p-value. So we're going to be able to compare p-value to alpha to make the same conclusion. So let's go ahead and calculate the p-value first. So this observation here, remember the p-value, the calculation is based on the test statistic, and we went over last class, the steps to actually calculating the p-value is we're gonna look at the observation, and relative to this observation that has this test statistic, we wanna find the area in the same direction as the nearest tail. So this observation is gonna have a right area and a left area relative to that observation. Do we wanna find a right area or a left area in this case? Which area is in the same direction as the nearest tail? Yeah, a right area, very good. Because here we only have a right tail, so that's the only tail, so it has to be the nearest tail. So because the nearest tail is a right tail, we want the area to the right of this observation. So now we're gonna find the area to the right of this observation. That would be the first step to finding the p-value. So this observation has a test z-score of 7.48. So what do you think the area of the right will be close to? Yeah, the left area will be 99.99% because the chart maxes out a 3.5 z-score. And then, so that's the left area, so what would the right area, which is what we're interested in, be?
Both zeros
Close
and
to
one.
zero.
Yeah, it would be 0.0001. And that's for a z-score of 3.5, but our z-score is way higher than that, 7.48. So our right area will be even closer to zero than that. So this right area will be virtually zero. So for now, because we can only use a table and can only have a rough approximation from the table, we'll say that this area is approximately zero. That's the first step to calculating the z-score. Calculating the p-value? What was the second step?
Multiply by the number of tails.
Yeah, we multiply by the number of tails. So in this case, what do we multiply by?
One.
Just one, because it's one tail. So it turns out that the p-value is this number that we came up with that represents the area. We don't, because multiply by one doesn't change the value. So the p-value here is virtually zero. It's almost zero. So for now, I'm going to say some number that's so close to zero, it's virtually indistinguishable from zero. Later on, if you needed a more exact answer, then you would use something besides a table, which can only give you an approximate answer. You would, sometimes your homework instructs you to use technology, in which case, instead of using a z-score table, you would use a z-score calculator. So you would Google, for example, z-score calculator, and the calculator will prompt you for the same thing. So you would enter in this test z-score 7.48 in the online calculator, and the calculator will spit out a left area for you that is much more precise than a table would be able to give you. And and once the calculator spits out a left area, you can easily calculate a right area. Or sometimes the calculator will spit out a right area directly for you. Any questions? Okay, but for now, the p-value, let's say, is approximately zero. So now, with this p-value, that's approximately zero, how do we make the same conclusion that with, let's go back to 95% confidence. So for 95% confidence, how do we determine whether the observation is inside the body or the tail?
P-value is greater or lesser than the alpha.
Yeah, very good. So always, after we calculate the p-value, to interpret the conclusion using the p-value, we compare the p-value to alpha. And we had that cute saying that we talked about last time, if the p-value is low, the null must go. So if we compare the p-value to alpha and it's lower than alpha, then the null must go. So this p-value is virtually zero, so it's gonna be lower than anything. So alpha, for 95% confidence, is 0.05. So if the confidence level is 95%, alpha is 0.05. So the p-value, if we compare it to alpha, which is 0.05, will be lower than alpha. And because of that, for a confidence level of 95%, we're able to reject the null hypothesis. So if the p-value is low, the null must go. But what about for other confidence levels? What about a confidence level of 99%? That means alpha is what? That means alpha is 1%, or 0.01. And again, you compare the p-value to alpha, but the p-value is virtually zero. So compared to alpha, which is 0.01, it's still greater. So in this case, the p-value is not low, so the null must not go. So, oh no, sorry. So in this case, the p-value is low. It's still lower than 0.01, so the null must go. The p-value is low, the null must go. Any questions? Questions? Okay. So this is a review of calculating the p-value and also using the p-value to reach the same conclusion of what to do with the null hypothesis. Any questions? Yeah.
So on the TED, would you prefer us use p-value instead of like doing all the steps?
Well, still, even if you use p-value, you would still have to do almost all of these steps. You would still have to go through these steps and then calculate z-test first. And then from z-test, you would do the two steps of calculating the p-value, which is find the area in the same direction as the nearest tail, which after you got z-test, then you would use the table to find the appropriate area. Then on step 2 of calculating the p-value, you would multiply by the number of tails, so you would still have to go through all the steps in calculating the p-value. And after you calculate the p-value, then you would interpret by comparing this to alpha. So really, you would still have to go through all the steps in calculating the p-value. But to answer your question, which one is preferred, the p-value is preferred. But you should still be able to know how to reach the conclusion by calculating the test statistic and comparing it to the critical statistic as well. So you should know how to do both. But in real life, the p-value is preferred. Any questions? Okay, so now that we talked about the p-value and why it's preferred, if somebody reports that their p-value is this number that is virtually 0, what does that mean? So in this context, again, we have this claim that over 90% of the world recognizes the brand. We have this distribution where we assume that it's true that 90% of the world actually recognizes the brand. And we have this observation of 971 that ends up having a p-value of virtually 0, which means it's very far right, and it's definitely in the tails. So what do you think this p-value of virtually 0, what does that mean? If somebody reported that p-value, what does that mean?
It's nearly certain that the null hypothesis is false.
Okay, very good. So let me phrase it maybe slightly differently, but what you said is correct. So this p-value, what that means is it's the probability of observing this observation, or an observation that is even more extreme than this, if the null hypothesis were actually true. So this is exactly what we're doing here. We're supposing that the null hypothesis is actually true, and that the proportion of people who recognize this brand is actually 90%. If this were true, then what's the probability that you're to be able to observe this observation or one that's even more extreme than this? So the probability of being able to observe this in real life would be virtually 0. So this is saying if the null hypothesis were true, the probability of observing this observation or something more extreme is virtually 0. So that means it's virtually impossible to observe this if the null hypothesis were true, and so therefore the null hypothesis can't be true. And so that's what the meaning of the p-value is. If the null hypothesis were true, what's the probability of actually observing what we just observed? And if the p-value is low, which is actually what we want, then we're able to reject the null hypothesis. Any questions?